Hello, everyone, and welcome to The Explainer. I am absolutely thrilled to have you here today. We rely entirely on this vast, invisible telecommunications infrastructure every single day of our lives, and yet most of us never actually stop to think about the incredible journey our data takes. Well, today, we're going to change that.
Think about this core mystery for just a second. How exactly does a high-definition video travel from a server on the literal other side of the planet straight to the screen in the palm of your hand, all in a matter of milliseconds? It feels like magic, but today we're going to demystify the dense, frankly fascinating engineering that happens right behind the scenes of your everyday devices.
So, here is our roadmap for today's data road trip. 1. Anatomy of a network. 2. The physical transmission highways. 3. Directing traffic with switches. And 4. Circuit versus packet switching.
Okay, let's dive right into part 1, anatomy of a network. To really understand telecommunications, we have to break it down into 4 basic parts. We've got end systems, transmission systems, switching systems, and signaling. Now, the journey of our signal always starts and ends in a very familiar place, with you. It starts with end-user instruments. These are devices you know intimately, stuff like telephones, cell phones, computers, even fax machines. Their whole job is basically to act as transmitters and receivers. They take the information you create, encode it into electrical signals or data bits, and then on the receiving end, they decode it back into a message you can actually understand. But what exactly are they sending?
Well, the amount of data totally depends on what you're doing, and the difference in bit rates is staggering. Think of it like different types of traffic requiring different amounts of road space. A standard digitized voice call is actually tiny. It needs just 6,400 bits per second. But if you want compressed video, suddenly you're looking at between 2 and 10 million bits per second, and full motion video, that demands a massive 1 to 2 billion bits per second. Just think about the sheer capacity required to go from a simple phone call to streaming a 4K movie.
Which brings us to part 2, the physical transmission highways.
Once your device encodes that data, it needs a road to travel on. So right from the start, our data hits a major fork in the road. It can travel on either guided media or unguided media. Guided media is exactly what it sounds like. The transmission relies on a physical, tangible medium, like a wire or a cable, that physically contains and guides the signal. Unguided media, on the other hand, is wireless. It provides a way for electromagnetic signals to travel freely right through the air, without any physical track at all.
And if we break these two classes down, we get our specific lanes. Under guided or wired media, we're talking about specific cable types like twisted pair, coaxial cable, and fiber optic cable. Under unguided or wireless media, we're primarily dealing with signals propagating through the air or atmosphere. Let's zoom in on a couple of those guided physical cables for a second.
This is where it gets super cool, because you can see an older technology sitting right next to a modern marvel. On one side, we have the twisted pair copper cable. Those two wires are strung together in a helix shape, and they're twisted specifically to reduce what engineers call crosstalk interference between adjacent pairs. It's great, cheap, reliable communication. But on the other side, we have optical fiber. This is literally a hair-width strand of glass or silicon, and instead of electricity, it uses light pulses generated by a laser or an LED. Because of a principle called total internal reflection, the light bounces off the inner walls, kind of like mirrors in a long hallway, which allows data to travel for hundreds of kilometers at a gigabit per second with virtually zero signal loss.
But, what happens when running physical cables across a massive mountain range or the ocean just isn't possible. That is where unguided media totally shines, specifically satellite communication. I want you to think of a communications satellite as basically a giant microwave relay station in the sky. A ground station sends a signal up, the satellite's transponder catches it, amplifies it, and then rebroadcasts it on another frequency straight back down to Earth.
To make this work, though, the satellite has to stay perfectly stationary relative to our stations on the ground. So we place them in a geostationary orbit right above the equator at an absolutely incredible altitude of roughly 36,000 kilometers. And because they need to be spaced out to avoid interfering with each other's signals, specifically, they can't be closer than 4 degrees apart, there's actually a hard physical limit. There can only be exactly 90 of these communication satellites in that equatorial plane at any one time. Crazy, right? But here is the catch, and it's an interesting engineering problem. Traveling 36,000 kilometers up and 36,000 kilometers back down is a 72,000-kilometer round trip. Even traveling at the speed of light, that massive distance creates a very noticeable 270 millisecond propagation delay. In an interactive conversation, that 270 millisecond delay is a literal speed bump. Actually, it's the exact reason for those awkward overlapping pauses you always see during live satellite news interviews.
All right, moving right along to part 3, directing traffic with switches. So we've got our data and we've got our highways, but how does a piece of data actually know where to turn to reach its final destination? Well, the history of switching is this fascinating mini-narrative of automation. Back in the 1890s, the intelligence of the network was literally human. Operators manually plugged cables into switchboards. But humans are expensive, slow, and, let's be honest, not always discreet. In 1892, we got the Strowger step-by-step electromechanical switch, where the user's dialing directly controlled the connection. By 1938, more advanced crossbar systems rolled out. And finally, in the 1970s, we entered the modern era, with electronic switching systems, or ESS, which are entirely computer-controlled through software.
At its core, whether we're talking about 1890 or today, a switch has one main job. It takes a signal entering through an inlet and connects it to one of a multitude of outgoing circuits. But it also has to do what's called busy testing. This is the traffic cop aspect. The switch has to smartly divert traffic or give you a busy signal if the road is full. It's doing this to prevent new calls from crashing into circuits that are already being used.
Which brings us to our final section, part 4, circuit versus packet switching.
We know how the physical switches function, but what are the actual rules governing how traffic is managed across these vast networks? Basically, there are two fundamentally different approaches. With circuit switching, a complete, dedicated path between the source and destination is fully established before any data can even be transmitted. Think of the old landline telephone method. You're essentially reserving a whole private road just for your one call. Packet switching, however, is the modern Internet's method. It groups all the transmitted data into suitably sized blocks, or packets. Instead of a private road, imagine chopping your data into tiny delivery trucks that just share the public highway with everyone else's packets all at the same time.
When you lay them out side by side, the operational differences are pretty stark. Circuit switching requires that setup beforehand, and it uses a continuous stream of data. But because that dedicated line literally just sits empty if no one is actively speaking, its overall network efficiency is way lower. Packet switching doesn't need that dedicated setup. The data is broken into blocks, and because everyone dynamically shares the medium, packet switching achieves vastly higher network efficiency.
Now, I should also give a quick nod here to message switching, because it was actually the historical precursor to packet switching. In message switching, an entire message is routed one hop at a time. The whole thing is stored, usually on a hard drive at the switch, before being forwarded to the next stop. It's basically a store and forward network. Email is a classic example of this, right? A slight delay in delivery is perfectly fine for an email, but it would completely ruin a real-time voice or video call.
So, for our modern real-time demands, packet switching is absolutely king. Like our sources point out, packet switching increases network efficiency, robustness, and enables technological convergence of many applications operating on the same network. This brilliant methodology, constantly directing millions of tiny packets over complex fiber and satellite highways, is exactly why your high-definition video arrives smoothly and perfectly reassembled in mere milliseconds.
It truly is a remarkable, invisible world we've built. It's like a giant puzzle constantly solving itself in the background. But it does leave us with a pretty incredible thought to ponder. As our daily data demands continue to just explode, from megabits to gigabits and eventually terabits, what entirely new type of highway might we have to invent next just to keep up? Well, I hope this explainer gave you a whole new appreciation for the epic journey of a single signal. Thank you so much for hanging out with me today, and keep exploring.